Everyone, good evening, good afternoon from around the world. Welcome to ICANX Talks, Connecting the World and the Universe. I am your host, Martin Thuo, coming to you from Iowa State University in the middle of the United States. In continuing with our April topics and biomaterials and application, we have had the young investigators early in the month, and then we had Professor Fulan from Australia, and last week we had Professor Rashid Bashir from University of Illinois, Urbana-Champaign. Today, we are privileged to have Professor Ju Li from MIT. And co-hosting with me will be Professor Arish Zhang from Peking University and co-founder of ICANX, Bara Diop from Senegal, and our ex-challenger is going to be Emily Lincoln from Iowa State University and Ames National Laboratories. Our speaker today is Professor Ju Li. He's an extremely accomplished scientist who is also very highly cited, doing a lot of work on high entropy alloys, energy materials, and understanding mechanics of materials at extreme environments. Professor Li has been a professor at Ohio State University, at Penn State, Pennsylvania University, and now as a chaired professor at MIT. He's a 2005 Picasso Award. He won the 2006 MRS Outstanding Young Investigator Award. He has been named in the TL35. He has been awarded the TL35 Award. And as I said, he's credited to one of the highly cited fellows, researchers. He's a fellow of the APS, MRS, and AAAS, and is a co-host of the MIT A+B Applied Energy Symposium. And he is going to be sharing with us some of his work in this field of energy materials. Professor Li, please share your slides.
Thank you, Martin. It's a great pleasure to be here to talk to you today. Thank you for the invitation. So I will talk about extreme material processing with application in clean energy. And I would first go through the sort of scientific part. Extreme processing uses radiation, such as a photon or gamma rays or electron beam, or things like microwave plasma or pulsed Joule current to drive the system far from equilibrium and achieve unusual states of matter. So to illustrate, this is a kitchen microwave, but under the drive, we can induce a plasma discharge, which is the lighting you see in the kitchen microwave. And if we so that plasma is induced by a carbon foam that we've made with collaborators. And the foam looks like this. So under the electric field, it induces a plasma discharge. And if we use a pyrometer to look at the color, we see that, so this foam is in a jar, and actually it's sealed in a plastic bag. So what you see is that you have locally very high temperature, approaching 3000 Kelvin, so 3000 degrees. And also we're inducing the decomposition of some plastic material nearby, but surrounding the plasma discharge is actually not very hot. In fact, the plastic bag is still intact. So this shows the ability of such extreme processing method to achieve very locally, very high temperature. So for example, in this case, we put these used masks on top of this initial carbon foam, and we're able to completely pyrolyze this mask. And we converted that 90% of the original organic mass to these small molecules, so hydrogen, carbon monoxide, methane, ethane. So these could be used as fuels or as precursors for later chemical synthesis. And this is in collaboration with Dr. Qiaojin Liang and Professor Zhu Meifang, where we have shown you can convert a whole range of waste organic matter into useful gases. And also we can, in the last 10% of the plastic material, is actually converted to carbon itself. So you have some kind of self-reinforcing foam, and in fact, the plasma discharge efficiency improves with the 10% solid carbon in the plastic waste. So we envision this could be a self-perpetuating process. Another example of this extreme processing is by a pulse of light. So what you see here is we can have a few joules per centimeter squared photon energy within a very short duration. This is in collaboration with Professor Yanliang Zhang at the University of Notre Dame to treat surfaces. And generally, our approach is we try to understand what happens at the atomic scale by doing characterizations such as transmission electron microscopy, as well as first principles modeling to try to get a grasp of the mechanism. And once we have the mechanism, we can go back and use active learning to tune the processing parameters, and hope is to be able to rapidly process materials at the macro scale. To give you one example, a few years ago, Professor Liang Binghu and we have collaborated in trying to understand what happens when you apply a very high temperature pulse to a material. So in this case, we just have a substrate where a pulsed electrical current is passed through it. And within tens of milliseconds, the temperature raises to more than 2000 Kelvin. And then we can also cool down very rapidly within tens of milliseconds. So what happened is that we initially put on this carbon substrate some chloride or nitrate salts. So we put multiple kinds of salts like platinum chloride or palladium chloride salts, and these salts are microns in size. But what we found after this thermal shock treatment is that it has decomposed into these nanoparticles. And in fact, what Dr. Yao have shown is that with this, we can mix up to 8 elements in a high entropy alloy. So platinum, tin, palladium, nickel, iron, gold, cobalt, copper. And what is very curious is that these metals, generally, they do not like each other. They usually do not mix into a single phase. Some of them like to be in the phase center cubic structure, some like to be in the body center cubic structure, some like to be tetragonal because they have very different atomic radii from 1.24 to 1.44 angstroms. And they have very different reduction potentials, boiling points, and so forth. But apparently by this very rapid processing, we were able to mix, let's say, 6 components, iron, cobalt, nickel, copper, together, all in the phase center cubic structure, sometimes have a stacking fault, but still in the FCC structure. And another thing that we noted was that the faster the carbothermal shock, the more uniform and smaller the nanoparticle size is. And that was quite surprising. For one, is that the temperature we're talking about is extremely high. At that temperature, these metal particles should be molten. But according to Ostwald ripening theory, these particles should actually grow at this high temperature to minimize the surface energy. So we don't understand why they are so fine nanoparticles. And to understand that, I have collaborated with Professor Zhi Weishan at Xi'an Jiaotong University. And this was actually a work that was done even before that 2018 work. It was only recently published, where we put some palladium nanoparticles on a silicon nitride support. And we then give it a temperature of 300 Celsius and also pass some oxygen gas in the transmission electron microscope. So the scale bar here is 20 nanometers. If we don't heat it or if we don't give it oxygen, then these palladium nanoparticles, they don't move. But what we found was that when there is both temperature and oxygen, they actually start to move. And that's quite surprising. And in fact, they move like these zombies. So initially only one start to move, and it actually have to sort of bite another particle which was stationary, and then that particle would move. So you can see here, this was the initial particle, it bites this particle, and then it start to move, almost like in a chain reaction. And with proper under-focusing, we see that wherever the particle move, it seems to clear some track here. And that was actually surfactant that was used to disperse nanoparticle on this TM grid. So we came up with an explanation of this effect, which is that initially, all these palladium nanoparticles are covered by carbon. And so this can happen in highly reducing environments in the, let's say, petrochemical industry, where these carbon sealed off the contact between the catalyst and the gas, and so it's inactive. But there is always one particle which has some flaws, and in this case, the nanoparticle will be able to react with the oxygen gas and going to emit carbon dioxide, and it's going to remove this carbon coating. And so this is free, and as it frees, it touch another particle and free the next particle, and removing carbon dioxide or carbon monoxide. So this process is very similar to human being. You know, we live because we eat, we metabolize carbon, right? And so, in fact, these catalysts are living. They actively consume chemical energy. And so our explanation of what happened was, initially you have these big micron-sized chlorides. And when we heat it up above 1,000 Celsius, these chloride first leaves. But then this Nico found that there is oxygen on the carbon surface, and it decides that by doing this fission, which means a big particle split into two molten liquid particles, it can have more contact with these oxygen on the carbon support. And so it starts to move around to hunt for these carbon groups on the surface, and eventually can fuse with the gold to become a gold nickel alloy catalyst. But this also have some catalytic activities. This can also split. And so you have this balance between nanoparticle fission and fusion. So you get a dynamic steady state when, as long as there is oxygen and carbon to be catalyzed. So we have two proofs for this theory. One is that we have run this mass spectrometry on the system. So the black curve is just the carbon fiber. And because we're heating it to 2000 degrees, even if there is no catalyst, it's still going to emit some carbon monoxide in the carrier gas. But what we found was that when we put this chloride salt, drop the chloride salt on the carbon fiber, the carbon monoxide peak come up faster. So this indicates there is indeed some catalytic activity of this chloride salt. And the second piece of evidence is that we actually have different kinds of carbon nanofibers. In fact, this temperature is not the temperature of heating. This is the temperature at which we pyrolyze the carbon. So this actually is a high quality carbon nanofiber with higher degree of graphitization. So less dirt on the surface, less oxygen, sulfur, nitrogen, and so forth. But in this case, we do not get good dispersion of this nanoparticle. It is actually this not so high quality, not so well graphitized carbon fiber, which have a very fine dispersion of nanoparticles. And to show that this all-sort of ripening is delayed, we actually have another example where what you see is this palladium nanoparticle not only just touch the other particle, it actually completely fused with it. I mean, there's a big, it's basically one particle. So according to the traditional Ostwald ripening theory, this should be, the more happy state. But then we found that later, this part and this part is split. And the reason is basically food. So this part, there's more carbon to be metabolized here, and there's more carbon to be metabolized here. And for that reason, there is after the fusion, there is a fission. So this shows this fission-fusion balance. And indeed, we found that this kind of living catalysis system having this dynamic equilibrium, you can use it to control the particle size distribution to below sub 5 nanometer if you give it plenty of food to metabolize, and also if the cooling rate is appropriate. So we found that, if you cool down very slow, then this gold and nickel can have phase separation. And so they can have enough time to do the solid partitioning in this time temperature transformation diagram. And later, if we expose this to oxygen or to water as an electrocatalyst, then this nickel can become nickel oxide or nickel hydroxide. So you would have a nanoparticle on oxide support catalyst. But if you cool down with intermediate rate, you would get this random solid solution phase where you get a high entropy alloy. And if you cool down really quickly, then it's also possible, we think, for you to get metallic glass. So by controlling the rate of cooling, you can actually get 3 outcomes in these nanoparticles. And my collaborator at University of Maryland have used, in fact, this quinary nanoparticles to catalyze ammonia oxidation, where the preferred products are these mononitrogen oxides. And so by having these living catalysts, they're able to greatly improve the selectivity of these mononitrogen oxide products. So in the last few years, we have taken further and this liquid precursor approach. So in this case, we're using a liquid handling robot to develop electrolytes, where we are mixing several salts with possibly several solvents, and we are measuring the ionic conductivity. So this was built by my student Zhichu Ren, I think 3 years ago. So after we measure the conductivity, he rings it and then dry it, and then do the next measurement. And so the main point is this. So generally speaking, we work in materials in a very big parameter space, right? So we can mix multiple salts with solvents. And let's say that we have done 3 experiments where the y-axis is some kind of a figure of merit. Now, in region where we have not yet done an experiment, there is big uncertainty. So as scientists, we are sort of naturally curious, and we will try to reduce the uncertainty. So exploration, scientific exploration, is all about resolving the unknown and reducing uncertainty, right? But as engineers, we also try to optimize the property. So we try to exploit the good results and maybe do more search in the already good performance regions. And that's called exploitation. And so because we are both scientists and engineers, the point of this demonstration is to show that the computer, using so-called Gaussian process regression and Bayesian optimization, can balance the desire for scientific exploration with exploitation, performance exploitation, and basically let the computer to choose what the next experiment to do. So the benefit of this is, number one, we can work in a very big parameter space without getting confused. It's actually much better than human in choosing the next experiment condition. And number two is this greatly reduces uncertainty, because humans are intrinsically not good at doing sort of repetitive experiments. And so by using a digital workflow, by having this laboratory automation, we greatly reduce the uncertainty. Is much more reproducible. And lastly, it's also the computer can work 24/7. You get more data points. And in the last few years, Zhichu have sort of taken this further, and by using this liquid robotics combined with the extreme processing that I showed you, using the liquid precursors, as well as high throughput, let's say X-ray diffraction and electron microscopy, we can perform these rapid experiments where, for example, this is a X-ray diffractometer which can get pretty good phase determination in 5 minutes instead of half an hour. This is the high throughput carbon shock. And in this plot, I'm showing that you can use this approach in addition to making multi-metallic particles. You can also use it to make oxides. So this is a lanthanum calcium titanium nickel perovskite material, and traditionally you need 20 hours in solid state synthesis to get phase purity. But with the carbothermal shock, we can get just in 55 seconds, we can get good phase purity powders. This is a samarium cerate, and recently we have, in collaboration with Professor Birger Yildiz, have shown that you can produce the raw material for solid ceramic fuel cells and electrolyzers by using this approach in minutes. And indeed, you can actually even sinter the powders to pretty high density. And by using this kind of voltage pulse, you can also induce exsolution of metallic nanoparticles embedded in these ceramic electrodes. So by using such extreme processing, very short duration, milliseconds, and sometimes even down to 10 nanoseconds, but pretty extreme conditions, you can achieve extraordinary microstructures in systems. And recently, in collaboration with Dr. Ding Dong's group, we have shown that you can build these proton ceramic solid electrolyzers. So this is used for water splitting, basically producing hydrogen gas from water using clean electricity, but also using stored heat. So for the first time, we're able to show good durability and operation down to 350 Celsius to produce green hydrogen as well as fuels and chemicals by this proton conducting solid electrolyte membrane systems. So we are also, in addition to this ceramic systems which work at intermediate or high temperatures, we're also making water splitters for room temperature anion exchange membrane electrolyzers. So in this case, we can directly distribute these multi-metallic nanoparticles on a carbon support, and we're able to get, let's say, up to 4 metals in one particle, and they're further anchored very deeply in the carbon. So you have very good binding with the carbon support, and it's used on the oxygen evolution electrode. And in fact, the performance of this quaternary nanoparticle beats the iridium oxide, which is the commercial available OER catalyst, and also is also more stable than the iridium oxide nanoparticles. And just in the last week, Zhichu have, with Zhen Zhang and another postdoc, Ali, have shown that by making these liquid precursors, we can drop them on carbon support. So, and then later, so we have multiple samples, and later we can do this extreme processing. And then we cut up the samples, load it up into these electrodes. So now we can pick up 1 electrode, and this is a 3 electrode experiment. We have a reference electrode, working counter electrode, and the working electrode is dipped into the beaker. And everything is automated. So look, someone is typing, but it's actually a Python script that Zhichu and Jen and Ali have written. And so this basically can do 20 experiments per evening, overnight, without any human intervention. After it's done, the robot take it out. And then we can try the next sample. And by collecting all the data, we can do the active learning and do the next batch of, let's say, 9 experiments. So with that, and in collaboration with Professor Sameh Osadi and also Professor Paul Koh at Georgia Tech, we're able to make an alkaline water splitting device with the anion exchange membrane electrolyzer at room temperature with very high current density. So this is close to the industrial requirement. 1 ampere per centimeter squared is very, very good at room temperature. And we're able to run for 550 hours at the membrane electrode assembly level with 1.85 volt. So the thermodynamic voltage is 1.23 volt. So this is really very good performance and very durable full cell system. So with that, I'd like to switch gear a bit and talk about sort of the bigger picture. So just this month, we get the IPCC AR6 report on climate change. In fact, the outlook is really not very good. It's actually, we're really looking at climate adaptation right now. And so it is well known that, even if we do the best we can do, we're probably facing a 2-degree temperature rise at the end of the century, if not much more horrible situation of 4 to 5 degrees. And to even sort of reach this kind of goal, it demands us to reduce the global CO2 emission, from 2020 level by a factor of 2 globally in 20 years, in 2040. In fact, only 18 years left. And the key word is global. So it's not just in the US, China, Europe, but it's also Africa, South America, everybody. And that in the face of economic development is really very challenging. And so according to the human experience, industrial development experience, there's really no time left for a baby technology, for new technology in the lab today to be able to scale up to tera scale to have an impact in just 18 years. So what that means is that you have to have both so-called A track. A stands for action, and I think A includes solar, wind, nuclear. That means light water nuclear reactors. In fact, nuclear was so far the biggest decarbonization demonstration in the 1960s and 70s thus far, and some battery energy storage, because only these things which you have seen, today have a chance of hitting this kind of scale in 2 decades. And so I organized this Applied Energy A+B conference, and the idea is to sort of provide timelines for what is type A technology and what is type B technology. So grid scale battery, battery management, and also recycling of battery waste. These, I think, are type A because there is a chance, as I'm going to show to you, of truly making a great impact if we make the right moves. On the other hand, fusion or fast neutron reactors, these are baby technologies that we need to nurture today because a baby takes 18 years to become adult and have an impact, and we still have to put effort into these for them to grow up and be able to replace maybe some of the dirtier technologies for the A-type technology after 2040. So in the spirit of that, I like to talk about this grid-scale battery storage. So this was so far one of the bigger battery energy storage stations, 1.5 gigawatt hour. That means you can store the output of one typical light water reactor by 90 minutes. And so quite significant in this building. And in fact, in the building, you see it's not very very densely packed. And what's also quite amazing is this was built in 1 year, and even during COVID. We know that productivity in the construction industry is not very good in the US. And so in fact, that is the biggest, like 70% of the cost in the nuclear industry is going to the formwork, and the carpentry in sort of pouring the concrete is spent in the construction. But in this particular case, because of the very modular designs, this was done during COVID period. And this is really driven by the cost reduction of lithium-ion batteries. So in 2010, the lithium-ion battery cost $1,000 per kilowatt hour, but by 2018, it has gone down by more than a factor of 5. And this was really driven by the electric vehicle industry. So already 4 years ago, there was more than 1 million EVs sold in China. And so that really pulled the battery cell and pack price down to less than $90 per kilowatt hour now. And also going from cell to the pack and to system, you have a factor of 2 to 3. So the pack cost is, let's say, around $200 per kilowatt hour. And generally, these systems, these container scale systems look like this. You have the battery cells, and you have the power electronics, which provide the grid, interface to the grid. You also have the thermal management systems. And there was a study where people have compared lithium-ion battery with other ways of electricity storage, such as pumped hydro, such as compressed air, such as the vanadium redox flow battery, mechanical flywheel, or hydrogen. And there are many other ones like lead acid battery, sodium sulfur battery, supercapacitors, and so forth. And in 10 out of the 12 usage scenarios for the electrical grid, going from energy arbitrage to primary, secondary, tertiary response to bill management, power quality, power reliability, the lithium-ion battery wins in 10 out of the 12 scenarios. So only when you have like a very rapid response, the primary response, you can use the mechanical flywheel or the supercapacitor. And then for seasonal energy storage, you need to use a chemical fuel like hydrogen. So what this shows that you really can have a big impact with these lithium-ion batteries. And my colleagues, Professor Jessica Truncic and Professor Yiming Chang, has a very good paper in June, which is talking about this equivalent availability factor. So what this quantity is the following, that in places like Arizona and Texas, where there is plenty of sunshine and wind power, if the battery system cost drops down below $150 per kilowatt hour, then this EAF can hit 95%. In other words, you can basically use wind and solar in 95% of time, which means 19 out of 20 days. But in 1 day out of 20 days or 3 weeks, we're going to have a wind or a solar drought, and the battery has run down, at which time you need to start your natural gas fueled power plant. And this is very similar, to people living in the New England area where, when you have a storm, there's often electrical grid blackout and you need a diesel generator for emergency power. And so the whole point is that, okay, we don't need to demolish our fossil fuel power plants. I mean, after all, why should we? These are already sunk costs, but we only need to use them in 1 day out of 3 weeks. And so that's actually very good news, right? If this is true, then we can indeed achieve a lot of CO2 reduction, and so we're pretty much quite close to this level. So what's the problem? Is the problem the battery cycle life? Now, battery cycle life is indeed quite important. However, because of the development in the electric vehicle industry, the battery cycle life have greatly improved through electrolyte optimization, which I will show a bit of our research later, through better electrode design and technologies like pre-lithiation. So in this demonstration, we can have graphite electrodes pre-lithiated by contacting with a metallic lithium foil and achieve much better stability as a battery anode in the lithium-ion battery. And so even though the battery cycle life is important, but really it is possible to hit cycle life like 20,000 cycles, even with pretty deep charge-discharge cycles. Is it mining or manufacturing? Well, indeed, this is a huge issue because electric vehicles, which weighs about 400 kilograms, is actually much more mineral intensive than the existing vehicles. They use 3 times more copper. And in fact, to make one electric vehicle, you need about 200 tons of ores. So you basically need something like 100 trucks to dig up the earth and process it. So, currently the market occupation of EV is less than 5%. So if we try to replace all the internal combustion engines by electric vehicles, that means another factor of 20 to 50 scale up of the existing lithium-ion battery industry. And that is a civilization scale endeavor because this is going to put huge burden on the ecology, on the mining, on the transportation, on the whole sort of economic system within the next 2 decades. And so it must be done right. It's not something that should be taken very lightly. But in the sort of ultimate analysis, it turns out that we are lucky. That roughly that on Earth, by combining with the hard rock and the brine resources, there is just about enough lithium to electrify the entire transportation fleet, and with some extra for stationary energy storage, provided that we do the lithium recycling, provided that we take the used batteries and then put them back through technologies in recycling to reuse them. And so what I try to say is that the showstopper is not mining, manufacturing, nor cost, nor cycle life, but there are 2 real problems. One is fire safety. So in South Korea alone, in a period of 3 years, there was 27 accidents. And that's just not acceptable because this is a huge liability and the cost need to be folded into the cost of stationary energy storage. And generally, this is the system layout of that grid-scale storage. And what is interesting is that the overall energy efficiency is 70 to 80%. And so that's pretty good in one sense. But the problem is whatever is wasted, right, 20, 30%, needs to be removed as heat. And that thermal management problem is really acute when you have a big battery. So the bigger the system, the more complex the system, the more dangerous it is. So in fact, sometimes the accident didn't start from the battery cell, it actually started from the cabling, from the electrical interfaces, from the power electronics. So this is from a cigarette-sized, very little battery in the electronic cigarette. Unfortunately, this guy was not hurt. And ultimately, battery is dangerous because inside you have these organic solvents, which are volatile. So they have high vapor pressure, but also your cathode material, these transition metal oxides, when you charge them to high voltage, they themselves can release oxygen. So they don't actually need external air to burn. There's a lot of fuels in the battery electrolyte in the anode, but the cathode has its own oxygen. And so very often you have something called a thermal runaway, which is initially very small, maybe just a few microns in size, but that gradually sort of self-amplify until you have this eventual explosion, you breach the packaging and you have a big explosion. And in our group, we are looking at liquid electrolytes. So one thing that we pay close attention to is this so-called Coulombic inefficiency, which is 1 minus the Coulombic efficiency. This is, let's say, if I deposit 1,000 lithium atoms to the graphite anode, it's like I save $1,000 to the bank. But when I extract the lithium, I only get 999 lithium out because one is taken by the bank as some kind of a processing fee and is sort of stuck on the anode, is deactivated. And so this Coulombic inefficiency is, for a lot of batteries, inversely proportional to the cycle life. So how many cycles the battery can store energy and discharge. And what my previous postdoc, Liu-Min Suo, have found was that when you use different electrolyte solvents and salts, this Coulombic inefficiency exponentially depends on the amount of fluorine in the electrolyte, called a donatable fluorine concentration. And therefore, by increasing the amount of fluorine, you can exponentially reduce the Coulombic inefficiency and increase the cycle life. And that's very good. And in fact, fluorine and also other electrolyte additives can also improve the safety as well. And fundamentally, this is because when this fluorine-containing electrolyte decomposes, it forms lithium fluoride, which is a very wide bandgap insulator. And so you only need to decompose a very little bit of liquid to have a passivating layer on the electrode surface to stop electron tunneling. And this lithium fluoride is stable both against lithium metal, but is also stable against even like 5-volt cathode material. So this is useful for passivating both lithium metal anode as well as a high voltage cathode material. And furthermore, lithium fluoride is mechanically very interesting that when there is no moisture, there was some study that shows that microns, and not actually single crystals of lithium fluoride, can actually undergo 27% tensile ductility. So as a passivation layer, it can tolerate this kind of stretching inside. And so we have shown that with more and more lithium in the electrolyte, we can have better lithium metal deposition morphology on the lithium electrode side, metal side, but also on the cathode side, we can sustain up to 5-volt without corroding the aluminum current collector. And so now we're using these automated experiments to design new electrolytes for different kinds of applications. And recently, in collaboration with Professor Jai-Mai Johnson and Professor Yang-Shao Horn, we have developed a high voltage electrolyte for this NMC 811 cathode, which allows us to charge up to 4.7 volt. So generally, we know that the higher the charging voltage, the more energy you can discharge. But usually the higher the charging voltage, there is more strain in the system. So this is showing the C/A lattice constant. So what happens is this NMC materials, these are so-called secondary particles, are porous and polycrystals. So at the end, 40% of the charge, this anisotropy goes from +4% to -4%. And so traditionally, people found that there is a lot of cracking in the system because this grain boundary is not an invariant plane. In other words, you have two adjacent crystals, but their grain boundary length is not preserved. And therefore, you're going to have a lot of stress and sliding in this region. So with synchrotron imaging, we can see that if we charge to 4.7 volt, then after 100 cycles, there's a lot of cracks in the secondary particle. But what we have found was that this is not a purely mechanical cracking problem, because all we have done is to switch, we keep the same electrode, the same loading, the same charging rate, and discharging policy just by changing to this sulfon amide-based electrolyte. This is done by Dr. Weijiang Xue, that we can greatly reduce the corrosion of the oxide, because what happens is, this transition metal oxide can dissolve into the electrolyte, and so we want to develop an electrolyte which have low solubility of nickel, cobalt, and manganese, but still allow lithium to have significant solubility and transport lithium inside. So we found that just by switching a different liquid electrolyte, we can greatly reduce the cracking in the system. And this proved that this cracking is not just purely mechanical, but it's a stress corrosion cracking. And so we can get much better high voltage cycling and also much better lithium metal morphology. And also the coating also works as well. So in this work, we show that by having a cobalt boride metallic glass coating, this coating can have a 0-degree wetting angle into the grain boundaries. So this cobalt and boron, it completely wets the grain boundary between the NMC particles. And that coating apparently reduces the amount of transition metal dissolution. So this is with uncoated material, this is with coated material. We see much less transition metal dissolution, much less corrosion, stress corrosion cracking. And so when we charge to 4.4 volts with this coating, we can have very stable capacity retention and good performance. So in the last sort of 5 minutes, I want to also talk about more system level issues. So one thing is, in addition, going beyond the battery chemistry, there is issue with softwares and sensors. So in a recent work, we've shown that by using a new network to study the data of discharge of battery cells, we're able to have a predictive model of the residual useful life by just doing very few cycles of testing. So what you see here is that you have some used battery, and some of them only have residual life less than 200 cycles. Some can still have more than 1,000 cycle residual life. So what we show that is that just by using one cycle of testing, you can get very good predictions of the residual life, but also more than the energy density, you can even predict the cycle by cycle voltage capacity curves. And this beats the human expert picked feature. So, human experts have previously used things like battery impedance or the difference between the two discharge curves and temperature rise and so forth to characterize the battery. But turns out that this deep learning approach is really good at predicting the future battery cell performance. And using this, we can reuse used old batteries and to do also better battery pack systems for load balancing. And also, you can do a lot in terms of sensors. And this is not my work. This is done by my ex-student Jin Yang in Professor Yi Cui's group. And so he's looking at this issue of graphite anode. We know that at fast charging, it can precipitate out the lithium metal. And that can induce local shorting, which is very tough to handle, very difficult to detect. But his insight was that when that happens, you actually generate some hydrogen gas. And hydrogen is actually very difficult to seal in. And that generally is a very difficult problem for hydrogen economy. But in this case, Jin Yang used a hydrogen sensor, and that was able to detect this kind of a thermal runaway phenomenon 400 seconds. So this is like 8 minutes before there is any smoke or even any heat signature on the battery cell. And so this was now installed in this kind of container scale systems, and it has demonstrated to work quite well. So safety is a huge problem, but there is also a problem with recycling. And in fact, this is really a very big problem, because a lot of the renewable energy waste end up not even properly incinerated, and they just end up in landfills, very often in developing countries. So there is some kind of environmental injustice going on in this issue. And generally speaking, pollution is a vector, right? Because CO2 is the most well-known one, but we also have microplastics. So we have these plastic islands which are floating in the Pacific Ocean. And then in the battery, we have the membrane, we have the packaging, we have the separators, which are plastics. We also have heavy metals like cobalt, nickel, these are toxic. We also have a lot of these persistent organic pollutants and so on and so forth. And so we really need to reduce all these polluting components. And just showing, there's a recent survey that I've done with Dr. Rachel Maidal and Dr. Foss, just in showing how bad it is. In fact, this renewable energy waste, REW, the recycling rate is even lower than plastic, is even lower than e-waste, electronic waste. So it's less than 20%, and much, much less than lead acid batteries. So lead acid battery is recycled at 99%. Because there's residual value in the lead acid battery. So when it is completely non-functioning, there is still finite economic value in lead acid battery. But in the lithium ion battery, so far with a lot of the batteries like lithium iron phosphate batteries, there's pretty much negative value in recycling that. And so right now, the recycling of these kind of battery is less than 10%. So there was a recent study that compares the amount of CO2 for producing new nickel manganese cobalt batteries, new nickel cobalt aluminum battery. So this is a Tesla battery. And this is a new lithium iron phosphate battery compared to recycling with pyrometallurgical, hydrometallurgical, or direct recycling. So it turns out that for lithium iron phosphate, you actually emit more carbon dioxide compared to manufacturing new batteries. And so this is really kind of bad for the recycling business. And generally, you have these kind of spent lithium ion battery packs, and the disassembly of this, unfortunately, is not fully automated because a lot of the battery packs are welded together. So you need a human to disassemble it, key parts of it, and then you shred it, and then eventually you end up with this kind of a black mass, which very often has both the cathode and anode mixed together. So currently we're developing technologies to sort of recycle this kind of waste black mass. And the dream is to have very cheap battery, less than $90 per kilowatt-hour system level, and which can cycle, let's say 20,000 cycles. So that's the cell. And then by doing light recycling, we can recycle it 5 times with a completely closed loop for lithium, nickel, cobalt, and all these fluorine and phosphorus elements. So nothing gets discharged to the environment. And by using this kind of recycling combined with solar, wind, and nuclear baseload, we can have a completely electrified economy where we basically do not emit anything, CO2, microplastic, heavy metal, all of these in a closed loop. So that's sort of the ultimate dream. And I'm now involved in a company called E-Ion that's developing this kind of recycling technologies. And so to summarize the talk, I've shown you some extreme processing technologies and science and material science, but then we really need to apply this knowledge very rapidly in the next 20 years because we're literally running out of time. And I do think that grid-scale battery is possible. In addition to electrifying all the, basically removing all the internal combustion engines we also need to electrify the economy. And that requires us to store the energy in all the pumped hydro we can get, but also in developing this lithium-ion battery storage. And then the issues are safety and recycling. And there is no showstopper in any of this. My sort of take is that we can do it, but we just have to, do a lot of material science engineering, chemical engineering, mechanical, mechatronics, even software engineering, just a lot of work to do in the next 20 years to make it happen. So with that, I'd like to stop and welcome questions.
Thank you. Thank you very much, Professor Lee. It's a great pleasure to hear from you. If you can stop sharing, I can share my slide so we can go to questions. And so we have two questions from the audience, and one of them is from Chia-Kyung Wu. The question is, dear Professor Lee, thanks for your wonderful talk. As you said, now EV is becoming very popular, especially in China, but I'm still concerned about the distance shortage of EV, like 100 to 200 kilometers per charge in the winter. Could you please comment on this from technology side? When or how do we overcome this problem?
Thank you. So I'd like to say that I think with autonomous driving, you really don't need personal vehicles. I think by ride sharing, you can actually solve this kind of problem, just by coordinating vehicles. That's sort of on the macro level, but on the material science level, this low temperature energy problem can be resolved by better electrolyte and better electrode development. So there is a lot that you can do on the materials level, but also at the system level. For example, by incurring so-called internal short circuiting. So by doing rapid preheating with another, let's say, power source, you can basically resolve this kind of problem. And we are already working on this active control, which is you really control the temperature actively, intelligently, rather than sort of taking temperature as a passive variable. So I think with the, so I think the EV industry is already over the hype curve. So even without any government subsidy, it's going to survive and it's going to grow. And I think this problem is going to gradually be solved for sure.
Very good. Thank you very much for your answer. The second question, great talk, Professor Lee. In the carbonized fibers, is the material purely graphitic or is it partially oxidized? What is the quality of the resulting material?
That's a great question. So in fact, if it's purely graphitic, it doesn't work. So those carbon nanofibers always have some oxygen, some sulfur, some hydrogen, some these groups on the surface. And what we found was actually the more dirty it is, the better dispersive power we get. Now, of course, when we try to use this system, try to make electrodes, we also need some electronic conductivity. So there needs to be a balance, between how dirty it is and then on the surface, and then how good an electronic conductor it is. But for the active catalysis, for this extreme processing, we actually need to have pretty dirty carbonized fibers.
Very good. Thank you very much for the response to the questions. Now we're going to switch to the panel, and let me introduce our panelists. Of course, our first panelist, Alice, does not need an introduction. For the new people in the series, Alice is a founder of ICANN and has been doing a lot of work to promote science in China and globally. A very well accomplished scientist, very well published, and serves in editorial boards of several journals. And if I continue introducing him, I'm going to take all the time. So Alice, I'm going to leave it at that.
Okay.
Our next panelist is Professor Para Diop Gom. Professor Bara is our first cohort of young scientists, awardees at ICANN-X. He's a professor at UCAD in Senegal, Dakar. in Dakar, Senegal, in Africa, West Africa. He has a background in solid-state physics and is one of the few people who have 2 PhDs, one from Senegal and one from the University of Western Cape in South Africa. He's a very well-accomplished nanomaterial scientist working on energy-related smart materials. He's also well-published and serves on the reviews of as a reviewer of several journals. He's also the chair of the 2022 African Material Research Society Conference, which will be held in Dakar, Senegal this year. Our ex-challenger is our very own Emily Lincoln, a student at Iowa State and also doing research at the Ames National Lab. She did her undergraduate in material science here at Iowa State University, majoring in polymers and ceramics. But for PhD, she switched to high entropy magnetic alloys, working with the widely known Professor Ivar Anderson. For a brief, Professor Anderson is the inventor of the lead-free solder, the solder in all our computers. So Emily is coming to us from a great legacy. She has also been involved in quite a few graduate student level engagement at the national level and also in here at the university. And with that, we switch to our panelists. And as is a tradition, we will start our questions with our ex-challenger, Emily. Any question for our speaker?
Great, thank you so much. And thank you, Professor Lee, for the fantastic talk. I was fascinated by the wide breadth of research that your work covers, not only here in this talk, but in other works as well. And you're tackling some very urgent material challenges that will help realize an efficient and sustainable future. I want to focus on the beginning part of your talk. I was particularly fascinated by your high entropy nanoparticle synthesis work. I have 2 questions focused on this particular topic. First, in your slides, you showed multiple examples of STEM EDS images of your high entropy alloy nanoparticles that displayed uniform composition within the particles. Statistical thermodynamics is certainly suggesting that overall the high entropy nanoparticles are stable and have a uniform chemical composition, especially noting your success of the catalytic performance. But I want to dive a little bit deeper into the details here. I was wondering if you're getting a minor degree of chemical partitioning, maybe on the order of 5 to 7 atoms or so in these high entropy particles, assuming maybe you have particles of, for example, for this question, let's just say 10 nanometers. If you are not having that chemical partitioning on that small range, how does your thermal shock synthesis process assure absolute chemical uniformity?
Great question. Yeah, I think there should be some partitioning or at least the surface segregation, because it was in the liquid state. It's a random solid solution liquid. And then our theory is that because of the rapid quench, there is not enough time for nickel and gold to partition by tens of nanometers. But certainly, I think just like you mentioned, this is driven by catalysis, and I think there will be maybe some nickel preference because nickel is more active on the surface. So indeed, I would say there is a gradation. Now, to have a fully partitioned, let's say a biphasic, a Janus particle, you would need to not only partition but also have a nucleation process to have another phase, and that probably would take quite a bit longer time, which we have seen on the order of maybe seconds to do that. So it does depend very much on the cooling rate in this time temperature transformation TTT diagram.
Great, thank you so much. Another question following that, one of the points that you mentioned in your slide is that also with the catalytic process, if that's helping you get these very small particles, and you were mentioning that, oh, well, these should be growing through Ostwald ripening or coarsening or something like that. And I totally agree. And I was also fascinated by that as well. Another aspect I was thinking about while you were talking about this is maybe the immense Laplace pressure that each nanoparticle felt that during the synthesis process. So on top of the rapid cooling that you just mentioned and the catalytic process, I'm curious if the Laplace pressure during the synthesis translates to the system having this almost existing in this deep metastability well, which also plays a role in the stability of your nanoparticles outside of your chemical uniformity. And I also, I read the paper too, and you were saying that these nanoparticles last, they can be stable for up to 11 months. And that's really impressive. So could you talk a little bit more about maybe more of the aspects of the stability? Maybe would Laplace pressure also be part of that as well?
That's a wonderful question. So this Young-Laplace pressure would also shift the melting point. So you would have a melting point that's significantly different from the bulk melting point. And so indeed, that's very significant. And that driving force actually would drive coarsening. They don't like to be in that highly pressured state. However, still, we did some order of magnitude calculation. This physical pressure is still less than the chemical free energy dissipation that one can gain by having more catalysis happening. So indeed, if we don't feed it these oxygen, then they will coarsen and they will stop moving, and they will actually get fatter and fatter coarsening in this coarsening dynamic. So it is basically like if they exercise, they get thinner and they're active. And the whole point is you have this competition between the physical Young-Laplace kind of driving force for coarsening balanced with the desire to have more surface area to do the chemical catalysis.
Great, thank you. Awesome. I will go ahead and pass it on to the other panelists, so I'm not talking the whole time, but thank you again for the wonderful talk, Professor Lee.
Thank you, Emily.
Very good. So now we go to the panelists. And Bala, you want to go next? You're muted. Bala, you're muted.
I'm okay. It's okay now.
Yes.
Okay.
Yes.
I just would like to thank Prof. Ju for this very, very, very exciting and informative, indeed, science, which really overlap with a couple of the work that we are currently doing here at University Cheikh Anta Diop of Dakar here in Senegal. And we are really concentrate on working on different material where we're using biomass as a starting material to develop advanced nanomaterial for energy storage application, roughly batteries and supercapacitors. I quite have just one question. The other one have been answered. It was one of the questions from Emily, and the other question comes just after the question about the graphite the carbonized samples, where there is a graphite. Prof has answered that there is now, if there was no oxygen and so on, and those other elements, it could not work. That is, I would like Prof to elaborate more on that aspect for maybe for the student that are watching us. Thank you very much.
Thank you, Bala. So actually, there were two sets of experiments. One was done in the in situ transmission electron microscope, and that was the palladium nanoparticle on silicon nitride. And in that case, we used some surfactant to disperse nanoparticles. Initially, we didn't know, was not aware of this. So that one is a hydrocarbon with no oxygen in the surfactant. So in that case, we have to have atmospheric oxygen and heating to 300 degrees, and then we see the palladium start to move. And that work was actually done like 2016. That was long before this collaboration with University of Maryland. So in that case, we saw that if we don't have the oxygen, then the particle does not move. So we sort of understand that this particle is moving and splitting just to basically catalyze the burning of the hydrocarbon surfactant with atmospheric oxygen. And then, so by the time, you know, I met Professor Liangbin Hu, and we sort of discussing about this, because he found this effect in the carbo-thermal shock. And what we realized was that this cannot be a vapor process, because when we look at all those metals, they have very different equilibrium vapor pressures, even up to 2000 Kelvin, because some of them have very high boiling points, and their equilibrium vapor pressure is exponentially dependent on the boiling point. But we sort of get similar kind of proportion as we get as the salt precursors we put on. So right away, we sort of felt that one should not be a vapor process, it should be a liquid-based process. And in that case, you know, we did this dirty carbon nanofiber and the clean nanofiber. I mean, it's relative, even though we call it clean, it's not really clean, perfectly clean. And we see the dirty fiber, you know, give this much smaller nanoparticles and more uniformly dispersed, and also this sharp rise in the CO that's emitted from the system. So in that experiment, in that experiment in 2018, we didn't give it oxygen gas because this carbon fiber have the oxygen on the surface to begin with. So now you mentioned, you know, biomaterials. I think generally, if you pick the biomaterials, and unless you go to something like 2500 Celsius, where you can truly get perfect graphitization, generally, you know, these carbonaceous materials would have quite a bit of these oxygen and nitrogen impurities on the surface. So I think those will be, I think, applied to this kind of fission scenario.
Yeah.
And one last thing I want to mention is that in this automated catalyst exploration, we also found that the wetting angle is very important. So you know, we can use water, or we can use ethanol as the carrying, you know, as the solvent. But depending on what kind of carbon you have, in fact, we got carbon paper from different suppliers, and they are all different. The way that the activity are all different. And also, even one supplier, we found that the wetting in different regions of that carbon paper is quite different. So I think as far as the catalyst development as a substrate is concerned, it really very much depends on the processing history of that carbonaceous paper, and having a good uniformity is actually key for getting good sort of consistent result.
Very good.
Yeah, thank you, Prof. That was so clear, and I really appreciate the work and the talk. Thank you very much.
Thank you very much.
Yeah.
Alice?
Yeah. Very nice talk. Actually, I learned a lot. It's much more, you know, than my imagination. And you mentioned that Liangbin was, you know, your collaborator. And actually, Liangbin was given talk years ago. Yeah, so she be 2 years ago. Yeah, that's we already have ICANX 2 years. So it was, I think, in the first 10 versions. Yeah, so his work was kind of surprise, you know, to everyone.
Really inventive and creative.
Yeah.
Liangbin is much more famous than me.
oh God, I don't compete with this.
He's a very good friend and very creative.
Yeah, Liangbin and you should be from the same university, I think, in China. Am I right? Yes. Yeah. So all smart guys. Yeah, I can say that. Yeah. So my question about you know, this for you is in the last part you mentioned about recycle. Yeah. Actually, this was really a big issue, because in many places the batteries and solars, all these things, you know, units are sometimes become trouble, right? Yeah. I mean, you know, Liangbin gave a very good examples. Can use these supernatural, you know, materials, yeah, to do something. So in your mind, is that possible? We in the future we use some kind of different, natural materials to solve the problem of in this field?
Yeah, so Bala mentioned biocarbon, and that's a very big field. So, for example, Liang made I think wood knives, right? So indeed, stronger than steel.
Any other candidates?
And there's definitely, in terms of making hard carbon, for example, in sodium-based batteries. And in making all kinds of electrode materials, and also we need conductive agent like carbon nanofibers and carbon black. So that's a key battery component. And I also want to say that there is also so-called upcycling, which is when you do the processing, you actually get new material which is higher performing than even the old material. So. In this battery recycling and upcycling, there is a lot that can be done because we have very limited lithium. Like right now, if we only recycle 10% of the lithium-ion battery, and number one, they pollute the environment if they're not recycled. And number two, we're going to run out of lithium to electrify our economy. There's just actually enough lithium. I do some calculations. There's just enough lithium for the 7 billion people on Earth, for everyone, to be able to have electric vehicles. No more than that.
Okay, that's really good. Also, we have some kind of research group was doing for the artificial leaves. This kind of works for the energy source. Can you comment on this? Did they contribute a little bit for this?
Yes. So that's actually the oxygen evolution catalyst that I've shown at the first part. We have done this water splitting electrolyzer, and you can either have the photon coming in and then the hydrogen and oxygen coming out in one system, or you can harvest the electricity by solar and then use the solar electricity in a separate system to do the electrolyzing of water. So I'm working on the electrolyzer part, and indeed, people have looked at the economy of green hydrogen, because so far most of the hydrogen come from steam methane reforming. So you take natural gas, you react with steam, at high temperature, and a pretty big, apparatus to get this blue hydrogen. But that's still going to have, CO2 emission. The issue with green hydrogen has always been cost. It's something like triple the cost of the blue hydrogen now, because of we have to use a lot of platinum group metals as catalyst because of the expense of building this electrolyzer. And I think with like this biomass, and also with new ways of making this membrane electrode assemblies, we can, number one, use less platinum group metals, and number two, really reduce the manufacturing cost. So this collaboration with Professor Paul Koh and Professor Saidi showed that. I think we have actually a very competitive anion exchange membrane electrolyzer that works at room temperature now.
Okay, that's really good. I think, for this kind of field, actually in China, maybe long time ago in the countryside, there were many kind of, these issues was coming up. But a big issue maybe is for the efficiency.
Yep. Yeah. So right now we can have 1 ampere per centimeter squared, which is really very high current density at 1.8 volts. So our sort of energy efficiency is already like 66%. So that's actually one of the best for electrolyzers.
Yeah, this can solve a lot of the problems, especially in the countryside. The cost can be reduced a lot. Okay, thank you very much. Yeah.
Thank you very much. Professor Lee, one quick question as we conclude this session. Very fascinating work, really amazing. And I think if I start asking questions, we would have like an hour, because you overlap so much with what we are doing here on energy and using what we call Flugo innovation or Flugo material processing. I'm coming back to the carbon and the way you're processing it. Have you explored the nature of the carbon from autotrope point of view? because I was looking at that experiment. I was saying there has to be a way. Either you're forming Q carbon or you have graphitic carbon and Q carbon forming in the same system, which would make those tubes super hard and super strong. Have you looked at any diffraction patterns or any allotropy in the carbon that you're making to see whether you're getting any Q carbon?
Yeah, I have to say that I'm no expert in carbon, and maybe we should talk sometime about this. I'd like to learn more from you. I mean, so generally, I know, what I know is that there's a lot of mysteries in carbon. I mean, carbon is a huge field, and there's so many different issues going on in the carbon, and they do have a very important control on what we get at the end. Just like I said, it changed the wetting angle, it changed how the particle dispersed. So, generally, we know there is some sp3, sp2, but then there's also this turbostratic disorder. They're not all aligned, the graphitic sheet. There's a lot of ways, which I think mysteries in the carbon that we use. So far, I haven't produced my own carbon very much yet. So I look forward to working with experts.
Yeah, we should discuss that. I would be very interested, because what we have done in my lab, and in line with what Barai is saying, we are moved away from carbon nanotubes to carbon macrotubes. And I was not aware of your work until I saw your paper. And it's very parallel to what you're doing, because we do some rapid processing, high energy to supply to flip the thermodynamic state of the material and allow it to go into a form that is not very easy to access without going to very high temperatures. So yeah, we should discuss after the talk. And for the interest of time, I would like to tag along a little bit here. So thank you very much, Professor Lee. Very exciting talk and very, very informative. And
Martin, is that possible? We can add one question from Emily. I think Emily does now still have some question.
Yeah, sure. Emily, you have one more question?
Sure. I just have a simple one. Do you have, could you speak more to how any plans you have for scaling up that rapid carbothermal process? It's really fascinating. So yes, I figured I'd ask.
Thank you. So we are now thinking of, these are done with these alligator clips. So we do think, because the time that we apply is pretty short, it is possible to consecutively, have like a conveyor belt of systems where we can apply this. So it requires like a supercapacitor banks, like bigger current density, and the temperature is pretty uniform, because you have radiative heat loss, so it's not by conduction by law. So I think it's actually probably scalable to meter-sized, sort of almost like a printing presses of these things with carbothermal shock in the future.
Great, thank you, Professor Lee.
Thank you, Emily.
Very good. Thank you, everyone. Thank you, the panelists. Thank you, our challenger. And so, Professor Lee, if we were somewhere in a podium, I would walk across the hall and hand you this. But since we're on the virtual environment, please accept this virtual certificate for your wonderful presentation. And we'll look forward to more interactions with you.
Thank you. Thank you so much, Professor.
Yeah, thank you very much. And I want to make an announcement that next week, we're going to be having our ICANX Summit from 26th to the 29th. All of you are invited. We have lined up a series of speakers from Jean-Pierre Sauvage, Stefan Hell, and Gang Chen, our very own Jagadish, David Lei, Jiadong Ding from Fudan, and Li Hong Wang from Caltech. And so on the 27th, we're going to kick it off with Jagadish and Professor Ping Hong from Beijing Sports University. And then on the 28th, we are going to have the lineup of Jean-Pierre and David Lei and Stefan and Lei Hong. And then on the 29th, we're going to have Jiandong Ding and Gang Cheng. Of course, Gang Cheng is a colleague of Professor Lee at MIT. And these speakers are going to crown our Spring Summit. And with that, I want to thank everyone. Thank you very much for coming. Thank you.